The first topic under non-coherent. Non-coherent binary. Non-coherent binary modulation. Right. So in this, first one is non non-coherent binary. ASK, that is amplitude shift key. Okay. So what we do, we start with the equation of the transmitted waveform of binary ASK. Okay. So the binary ASK waveform S of t is equal to, we are sending a signal whenever the symbol is 1, and we are sending a 0 when the symbol is 0. Correct. So you are shifting the amplitudes, right? So amplitude is going to be a cosine wave whenever the signal that I want to send, or the symbol I want to send, is 1. Okay. And you are not going to send, you are turning off, right, the device whenever you don't want to send. Okay. So, or you want to send a 0. So that means S of t is equal to 2 times EB by TB under root times cos of 2 pi fc into t. Fc is the carrier frequency, right? So this is 0 less than or equal to t less than or equal to TB. This is for symbol 1. Okay, so at the same time this is 0. Again the duration remains same, 0 less than or equal to t less than or equal to TB. This is for symbol 0. This is what we already have studied. Okay, now, and our intention is now to make this as a non-coherent case. So what we can do now, let us assume that this signal, whatever it has been sent, right, goes through the channel and gets received by the receiver. And we know that we are not going to get the exact what you call the signal will not remain same, signal will remain slightly different. Correct. There is a noise component, or there will be some slight modifications, correct, in the signals whenever the signal, transmitted signal, reaches the receiver, right? So because of that, now let us assume, right, so let symbol 1 was transmitted and it is received in the form of x of t. Let the symbol a symbol 1 gets received in the form that is x of t. X of t is equal to square root of 2 eb by tb. We have the cos function as it is, cos of 2 pi fct. The first effect of a channel is in terms of adding a phase to the signal. Okay, so because of that, I'm going to enter a value theta to this. So 2 pi fct becomes 2 pi fct plus theta. Okay, that's the first effect. Plus the noise component that is getting added up, we can write AW of t. Right. now you see, this is for symbol 1, correct? When symbol sent is 0, what I'm expecting? I'm not sending anything. So this becomes equal to 0. I'm not sending anything. Only W of t will be received, correct? So it means symbol 1 gets received in the following form, right? And I can write symbol 0 gets received in the form that is x of t is equal to W of t. All right. Now, the receiver structure under these conditions, when you don't know what is the FC, right? We are going to use what is called as a uh, the receiver is called as matched filter. Okay, it's a matched filter type of receivers, right? So when you don't know what kind of FC, right, you are using, you can use a specific type of receivers called matched type of receiver. It actually uses a matched filter inside. Okay, so no, normally impulse response of the matched filter is right very similar to this function, that is root of 2 by tb into cosine function. It will be very similar to that. Okay, so let's look at that concept now. Then we'll write the block diagram, right? So such symbols can be detected by a receiver which uses a matched filter. Right. So when we say matched filter, right, it has to have a specific type of impulse response. Okay. So impulse response of the matched filter has to be in the form. The form is pretty straightforward. So we can write the h of t. H of t is the impulse response of a system. This is s of capital TB minus t. So s of t I know, I just have to replace t by capital TB minus t. So this becomes equal to root of 2 by TB into cos of 2 pi fc. Instead of t I am writing TB minus t. Okay, this cos theta is done, plus the change in the phase, right, plus theta, right? Now you see the very basic characteristic of a matched filter is that it is the matched filter is actually a LTI system. It's a linear, right? I can see that T is equal to TB minus T. So you have a LTI system. Its output can be simply obtained by convolving any x of t which is input, right? Input gets convolved with this h of t to get your output, right? So that's the very basic idea of a LTI system. So if you have a LTI system, right, simply you can convolve, right, to produce an output. We use the similar concept now in this. Okay, right. Therefore, the frequency response of the matched filter is also a very well-known quantity. We are going to write now. Okay, so let's directly write the required filters first. So all right, let's write the non-coherent binary ASK receiver. Okay, so we have the input signal. This is the receiver. Only transmitter is not required now, because anyway we know that transmitter remains same in case of a coherent or non-coherent modulator, because you just have to generate a modulated wave through the modulator. So you don't change the modulator structure at all. Only the receiver, on the other hand, now does not know what is the FC value. Okay, so it is expected to design the receiver in a different way when the different does not know to generate the phi 1 of t or phi 2 of t or any of the other signals. Okay, right. So let's directly write the receiver. Let's look at the receiver. Okay, so receiver looks like it has a antenna. There is an incoming signal to this. It picks up the signal. Let's call that signal as x of t. Right. Now, inside the first part itself, look at the difference. Previously, we had a multiplier circuit here, which used to multiply the received signal with the phi of t, right? The basis function we used to multiply. But now I don't know what is the phi of t, so I have to use a matched filter. So matched filter is normally matched to the following equation, that is root of 2 by TB into, this is cos of 2 pi fct plus theta. To this you use a matched filter. Again, this could be 0 less than t less than or equal to t. Okay, this is the matched filter that is present at the first. Okay, then the matched filter actually convolves x of t with this matched filter's impulse response. Okay, and it produces y of t. Okay, now the y of t has to be passed through another circuit that is called as envelope detector. It will pass through an envelope detector to get the envelope of the signal being detected, right? Once it passes through this, it comes out, it will be sampled out. So we have to sample. This sampler circuit will sample the signal at every instant t equal to tb. Okay, t equal to tb, this will be sampled. And now this sample signal will be passed through a decision making circuit. So the decision is based upon threshold. Okay, so it's going to check the, okay, it will pass through a decision making device. So the, it's going to use a threshold, that is BTH. Now let us say the value that comes here is L, okay, after sampling. So now the decision will be made up using the following technique. Let's say we have the binary data that will be equal to, so you have 1 or 0. So it is going to be 1, right? Whenever the value L, right, L is less than VTH. Okay, so this is the reverse of whatever we follow now. So L is less than VTH, you will decide that as 1. Okay, whenever the L is greater than 0, you decide that particular binary data to be 0. Okay, so here the matched filter's frequency response shows that it is actually centered at a frequency f naught, right? That frequency is 2 by TB, whatever TB we have used, right? It's 2 divided by TB, that's a frequency. The band pass, it's going to be located with the central frequency f naught given by 2 by TB. So we can try to extract that by using a band pass filter, right? So at the same location, right? So okay, so we'll write that point now. The frequency response of matched filter is a BPF, right, which is band pass filter with center frequency f naught is equal to 2 divided by TP. Okay, so it means whenever it comes out of the matched filter, you get a y of t, right? uh, we try to detect what is the maximum value, right, or the envelope of that signal y of t, right? So when we try to find out that envelope and it is sampled at particular time t equal to tb, right, uh, you can see that the decision is made in such a way that if that L value greater than VTH, decision is in the favor of symbol 1, otherwise decision is in the favor of symbol 0. Okay, all right. Again, we actually have a derivation corresponding to the uh, average probability of symbol error here. Okay, so which can be, is it okay? Do you have any doubt? Yeah, sure. All right. Okay. The next concept, before going to the sorry, non-coherent FSK and PSK, we need to look at a special, completely different type of receiver. So that is because for a FSK, we are sending two different signals, S1 of t and S2 of t. Right. So you see, whenever we are trying to send two different signals, right, during the modulation, right? The receiver which we just now considered is not going to work because it's not capable of identifying two different signals, as we have only one matched filter present over there, right? So for such reasons, for complex modulation, slightly difficult modulation technique like FSK, we have to go for a different type of the receiver. Okay, so that receivers are actually called as the matched filter, but using what is called as a binary orthogonal modulation. All right. So because FSK falls under a binary orthogonal modulation, you can see that there are two phi values. Correct. One phi was along x-axis, phi one, other one was phi two along y-axis. Right. So two basis functions which were orthonormal, they have been used. Right. Since they are orthogonal and normal to each other, you are saying that first. Then we'll try to sorry, yeah, we use the filters which are basically we try to use two matched filters, but matched filters are not designed directly. You use a correlator inside that. Okay, there is what is called as a correlator, and we use the correlators to do this job. Okay, right. So we'll move on to the next topic. This is not the demodulation of the FSK directly, non-coherent FSK. First, we look at the general structure of some sort of receivers, then we'll move on. Okay, so this is general topic, that is non-coherent orthogonal modulation. One such application we already have seen in the form of FSK, but we never knew that it falls under this particular category. Okay, but all right. So first, let's yes. See, he yeah, sure. I'll repeat. Okay, so now when I say non-coherent orthogonal modulation, right, there will be two or more symbols to be transmitted on mutually perpendicular axis, like phi 1, phi 2, phi 3, right? So we already have seen one such application in the form of ASK, not ASK, my mistake, it's FSK, right? In the form of FSK, we have seen. Right, but that was a specific case. Now we will see all such modulation techniques in under one side heading, right? And we will consider the equations in the general format, not a specific case like FSK. Okay, all right. Now, so if at all we use a binary signaling schemes where zeros and ones are represented by two orthogonal signals, like S1 of t and S2 of t. So we'll write let we can say the symbol 1 is represented by S1 of t, symbol 0 is represented in the form of say S2 of t. Okay, S1 of t and S2 of t, two different symbols and two different. Okay. And let us make another assumption that they are uh, having the symbol duration 0 to t and equal energy, some E you can assume. Okay, anyway, we are not writing that, we already have used this, so we are familiar. Okay, so now our intention is that we'll try to write the condition, right? You are choosing the S1 and S2 in such a way that, right, you see the orthogonal concept has to come, and in orthogonality we know that perform if you take the product of two signals and integrate the product over one period, right, answer should be either zero or it should be energy of the signal, correct? Root EB into root EB, so EB should come, right? So that's what. So this implies for orthogonality, this is the condition, integral 0 by the channel. Yeah, sure. Please take your time. Change in phase. So the theta was defined just to indicate that it is an angle, and it that's the change in the phase. Okay. It- yes. So if it is, if generally the equation was cos omega t, right? Uh, for phi 1 and phi 2, right? You might have used the cos of omega 1 t for first signal, cos of omega 2 into t for the second signal. So both the signals will be changed to now changed to cos of omega t plus plus or minus theta, right? And cos of omega 2t plus or minus theta, plus or minus theta. Something will change. Okay, it can be different at different point of time, and the value of theta basically depends upon what type of channel you are using, right? And what type of outdoor conditions you have. Many things will matter over here. Okay, while deciding what exactly is the theta value. It also depends upon what is the signal strength and what type of noise sources are present in the uh, channel. Is it outdoor, is it indoor, right, etc., right? uh, how many number of us, how many types of scattering happens, right? How many copies of waves will be generated by the modulator, right? And how many there is what is called as a multipath, correct? Those concepts will be used ultimately at the end when when the signal reaches receiver, right? How many copies of the original signals come to the receiver at a given point of time? It depends on even that. Okay. Okay. Now we understood that two components are added. One is theta and one is W. So the W is actually called as a noise process. Okay, so it's like if you remember the random process which generates a random variable, right? So capital X will be the random variable and small x will be the values that it can take. Correct. Now, very similar idea. So small letter w of t is the uh, noise that it gets added, right? Which is a function of the Gaussian process w, capital W of t. So I'll write only that point here because others we know now. So w of t is a function of the, again we assumed Gaussian, so I'll write the word the Gaussian process, capital W of t. So small w is actually a value. Capital W is the whole function. That function can take different values at a given point of time t, right? Again, it's a noise, so you cannot write an equation, but definitely it's a random function. Okay, that is W of t is a function, and small w of t is a value of that function at a given point of time t, right? But yeah, so point to at a point time t, right? Again, so we come back to the uh, basics of orthogonality. So since the S1 of t and S2 of t, both of them are supposed to be orthogonal to each other. So what we do, we have to choose the phi 1 of t and phi 2 of t in such a way that, right, they are going to have unit energy, right, and they are orthogonal, right? So you call them as orthonormal basis functions, right? So I'll quickly write that S1 of t and S2 of t are orthogonal. This implies, right, I have to select phi 1 of t and phi 2 of t such that, what are the conditions? They have to have unit energy. Okay, that's what is normal. When I say normalizing, it means you are trying to make the highest value as 1. Okay, so this has to be the case. Both of phi 1 and phi 2 has to have, they have to have unit energy, first case, and they are orthogonal. Okay, right, these are the two conditions. Now you see, phase of the carrier is completely unknown to us, right? So now we come to the receiver side, and on the receiver side, you received the signals, but you have no idea about the carrier's phase, correct? Because some carrier frequency is present and it has been changed by a specific value theta by the channel, so we have no clue, we are completely clueless, right? But still I have to uh, design a technique so that you come to know about what is the phase that is added by the channel. Try to remove the phase from the received signal so that the phase has been compensated, and you try to extract the frequency component fc from there so that you can process. This is our basic idea now. Okay, right. Now what we do, we have two different schemes of non-coherent receivers, right? So first one is pretty straightforward, we already have seen that, that is for a simple case like matched filter based envelope detectors, right? So we have seen them. Okay, now we try to use uh, two matched filter for a complicated like cases like this. Okay, so I'll try to write the answers now. So matched filter based demodulation or demodulator. First, let's look at this. Then we replace the matched filter by something more efficient called correlators. Okay, so this is the first idea. It's actually the simplest one. Whatever we have used in the non-coherent ASK demodulation, we repeat twice. Okay, that is because we have two different signals. S1 of t and S2 of t are the two symbols which can be received whenever you are sending FSK, for example. Correct? Okay, so what we do now, let's say we have an antenna and it receives the signal, and let's denote that received signal as x of t. Now since you have two different what you call possibilities, right, this gets divided into two channels. Okay, so assume, if you assume that you were having something like ASK, I had only one part of this. Okay, because either you send s of t or no s of t like 0, right? Now we use a similar concept here. Either you have phi 1 of t or phi 2 of t, like S1 of t or S2 of t being sent on the other side. So when S1 of t is being sent, I have to use a matched filter corresponding to the phi of t you sent for that particular S of t. Like, right, S1 of t has a orthonormal basis function which is phi 1, correct? So what I do, I design a matched filter, for the phi 1 of t. right? Because I'm trying to get the details of that signal over here. Okay, that's one. Then you go for an envelope detector. It's the same circuit. That's why I told this is pretty simple. Okay, but in order to increase efficiency, we have to replace the matched filter by something else at a later stage. Then you can see that we have the sampler. At every t equal to tb, you try to sample it, right? Then let's write the lower half, then we'll come back. Not in this case, okay? Not in this case because it's a receiver part, right? So only on the transmitter side I have to have. So here, yes, yes, yes. So we are not generating two different signals. One signal is received. I just have to decide which one is this. See, I'll come to that. I'll come to that point now. So let me write this, okay? Uh, Matched filter for, now I write phi 2 of t. The matched filter concept itself is designed in such a way that you don't need the NOT gate. Okay, I'll come to that now itself. Okay, just 1 minute. Let me write this. There is another envelope detector. Yeah, since it is orthogonal, whenever you take a product, right? So only when phi 1 comes, if this is phi 1, let me say the x of t is s1 of t, then only this will produce an output, this will not produce. So you don't need a NOT gate, correct? So at the same time, if assume that the received component has a phi 2 over here, then only this will work, this produces, it will not pass through this, right? So is correct, correct. So filter's response is matched to a specific phi 1 or phi 2. So matched filter's output depend upon what has been received, all right? Okay, then we have a sampler at t equal to tb to produce this. Now, what we can do, let's try to write a decision based circuit. Okay, so this is decision device, and this device takes inputs like this. So let us try to write the values like this is L1, this is L2. So the decision is 1 if L1 greater than L2. Okay, decision is 0 if L1 less than L2. So ultimately at the end we are generating a sequence of binary numbers. Okay, so we understand that S1 is transmitted corresponding to symbol 1, only the upper path will work, right? Because it is matched to 5, right? At the same time, if we have the low the 0 symbol 0 was sent using phi 2 of t in the form of s2 of t, the lower part of the circuit will work. Okay, that will be enabled automatically because of the presence of the matched filter. So second matched filter, which is the lower half of the circuit, that will work and that will generate something. So definitely, right, you can see that there may be L2 which L2 value will be greater now because L1 may not be present at all. L1 may be 0, right? The lower half of the circuit will produce a bigger value compared to L1. So that is L2 bigger than L1, indicating that the symbol will be decoded as a 0. So the decision here, we don't need any other threshold. Using L1 and L2 itself, we can decide that whether symbol 0 was sent or symbol 1 was sent. Okay, so this was the first technique, right? First type of demodulator that uses two matched filters. Okay, for orthogonal modulation was carried out, but we are trying to look at the orthogonal demodulation here. This is the first technique. So second technique is that we try to implement what is called as a quadrature receiver. Okay, so this second technique is called as receiver. So yeah. We have many applications. So anything other than ASK is considered to be the simplest one. Okay. But when we go for slightly complicated techniques, which uses multiple symbols, like you, as you told, if we go for QPSK, we have quadrature, which indicates more than two symbols present, like 4, 16, 8, etc. Right. So when you have such, you see the constellation diagram also becomes very complicated over there, right? So under such cases, when you have multiple symbols, we expect multiple phi values, right? Many phi values to be present so that each of the symbol can be represented over a phi value. And again, we are expecting orthogonality, orthonormality coming into picture, and it makes things very complicated, right? Under such cases, the demodulator, which should be very efficient, and it should be able to capture the signal and decode it properly, right? So we use a slightly complicated circuit that is called as quadrature. Okay, so the circuit is called as quadrature receiver. Again, now we'll see the quadrature receiver only for two different symbols. Okay, right. So this uses the concept of cross correlation, right? We use the cross correlation, right? Using them, we try to decode what exactly has been sent. Right. Now, what do you mean by cross correlation? If you remember, uh, correlation is a specific process in digital signal processing, wherein we try to find out the similarities, right, of signals, various signals. That's a correlation, right? So the correlation is a process. It's we have an equation very similar to the convolution over there, where you don't flip the signal, you keep both the signals as it is and perform the convolution, right? That's what is the basic idea behind the uh, correlation. Now, depending upon what signals you use for correlation, we have varieties of correlations possible. First one is autocorrelation, where you try to correlate a signal with itself. Okay, autocorrelation, auto indicates it with itself, right? A signal you have, and let's assume that I have a copy of the signal, but it is shifted, right? Signal with itself, the itself will have a shifted shifting component, like I have x of t and x of t minus t naught. Okay, t minus t naught, so depending upon the t naught value, it can be left shifted, right shifted, or something. Okay, when we have that, right, when we have that kind of correlation, this is called as autocorrelation, right? And the second technique is the correlation between two completely different signal. I have x of t and y of t. Okay, and I want to find out the similarities, right? So in such case, right, I correlate the two signals, right? And since you are performing the correlation between two completely different signals, right, this falls under the case called as cross correlation. Okay, so now we are using the cross correlation concept inside the quadrature receiver for demodulation of the orthogonal modulated signals. Okay, that means let's directly write the diagram first. Then I think we can extend this. So a receiver diagram. Okay, transmitter will remain same like earlier. Yeah, quadrature receiver diagram or the demodulator. Okay, you have a received signal that is coming up and it is denoted by x of t. Now, so again, this is divided into two channels. So I'm writing the first channel now. So the first channel itself gets divided into two parts internally. Okay. So the first part of the first channel is going to be a multiplier like say phi 1 of t, and I also multiply the same signal by its phi 1 cap of t. I'll tell you what is phi 1 and phi 1 cap later. Okay, then I go ahead and perform integral 0 to t dt, and I'll do the integration here as well. Integral 0 to t dt. This itself is the correlation. Okay, since you are performing with the x with phi and x with phi cap, this is cross correlation. Okay, we are not doing the x with x itself to say that it is auto correlation. This is cross correlation. So we have two of them, then followed by we have a squaring circuit, right? So this is a squarer here and another squaring circuit here. So both the squaring circuits are then combined to, we can use a summer circuit. Yes, this is plus. Now we get a value that is going to perform a square root. So this output will go to the decision maker, which for which we need to write even the lower half. That is, let's go back. Phi 2. So this will be repeated again with the phi 2 as the second signal that we need to consider. Okay, so this is I'm going to multiply with phi 2 of t. Then you have integral 0 to t dt. This output you are going to pass through a square. Okay, same thing. Multiply this with phi 2 cap of t. Perform integral 0 to t dt. Perform a squaring operation by using a square. And now we'll club these two results using a summer circuit. this now needs to be passed through a square root taking circuit, and we'll combine the results using decision making. So we'll write decision making circuit. So let's club the results. This is the first one. This is the second. Okay, let me give the names of various components. Here, when I multiply with phi 1 itself, the result of a squarer is called as, it's referred to as in phase component. Okay, so this is I for in phase 1 square, because there is output of a square. Okay, and this is x cube. You see the name is quadrature. Okay, x cube 1 square. So this is x I 2 square. And the other one I used phi 2 cap as a multiplier, right? So this is x q2 square. Now by clubbing the x1 square and x2 square, I got simply x1 square. Okay, or okay, we will give a name as in terms of L, because we are using L to identify the, so you can call it as L1 square. Similarly, the lower half we call it as a L2 square. So then you have a square root. L1 square becomes simply L1. This becomes L2. So we use right. We will be using the condition like this. So this is going to be 1 if L1 greater than L2. This will be 0 if L1 less than L2. Okay, very similar concept, but we have a name now to given. To be given. So you see, whatever I write inside the red color is a cross correlator. So this part is a cross correlator circuit. This part. You multiply and integrate. Yes, till the integrator is a cross correlation. This part is cross correlation, right? Again, there is another cross correlator that is present over here. So we used two cross correlators basically. Correct. So we replace the matched filters by the correlators. In this case, to get the same thing, right? The working is pretty much similar, right? And we get the values. You multiply with phi 1 and phi 2. If phi 2 is present, right, only the lower half will work, right? And if the phi 1 is present, the upper part of the circuit will work. Right, so they generate the different levels L1 and L2 accordingly. Okay, and finally you get the value like this. All right, and we use these circuits, right? Either the maybe a matched filter or the using the cross correlator to detect the FSK. All right, so we will be looking at the FSK modulator in the next class.